Hello everybody, my name is Mladen Knežić. I'm coming from the Faculty of Electrical Engineering, University of Banja Luka. And on behalf of my co-authors, I'm going to present a paper entitled Towards Implementation of Frame Preemption Mechanism on FPGA Platform. First, I would like to introduce you with an agenda. So first we will provide an overview of TSN technology and motivation behind our work. Then we will talk a little about frame preemption mechanism. After that, we will discuss obtained results of our design, and finally we will conclude this presentation and provide some directions for our future work. So first thing we want to discuss is actually what is TSN. TSN is a short for time-sensitive networking, which is an evolution of previous standard called audio-video bridging, or AVB. It is actually a set of standards driven by various IEEE working groups, which can be identified by three main components. Time synchronization is the first component, which is responsible for maintaining the common sense of time for every device in the network. Scheduling and traffic shaping is the second component, which is responsible for enabling determinism in the network. And finally, selection of communication paths and fault tolerance is component that guarantees the reliability of the network. All in all, TSN is aimed at providing a deterministic and reliable behavior of Ethernet-based networks. Our motivation is to implement the frame preemption mechanism, one mechanism that is used to support scheduling and traffic shaping on an affordable FPGA platform. We want to rigorously verify the correctness of operation of implemented design and to also enable a seamless integration with existing Mac implementations. Let's talk a little bit about frame preemption mechanism. So it is described within two standard documents, IEEE 802.1 management layer and IEEE 802.3, which is more related to Ethernet MAC. So it is basically introduced to mitigate negative effects of guard-band. I will talk about guard-band on the next slide. And it actually defines two traffic types, which are differentiated by the VLAN tag PCP field or priority field. These two traffic types are called preemptable and are designated as special M packet, and express, which is normal Ethernet frame. In principle, in TSN, communication is divided into cycles. So every cycle is further divided into sub segments or intervals, time intervals, with low priority traffic and high priority traffic designated as green and red part of the cycle. But between each cycle or between intervals within previous and the next cycle, we need to prevent that low priority traffic comes into high priority traffic, because it will delay sending of high priority frames, which is unacceptable. So in order to avoid this, guard band marked with blue color is introduced. So in order to guarantee that the largest possible frame will not enter high priority traffic, we need to reserve something about 123 microseconds for the largest Ethernet frame on 100 megabits per second. So in order to reduce this guard band, because it introduces the inefficiency in terms of bandwidth exploitation, we must enable a mechanism to preempt sending of a low priority frame marked with part 1 when it comes time for high priority traffic to be exchanged. So in this case, frame preemption mechanism differentiate low priority traffic or preemptible traffic and high priority traffic or express traffic. In order to support that, it provides two MAC units, EMAC for express traffic and PMAC for preemptible traffic. In order to reassemble preempted frames, there is a MAC merge sublayer responsible for that. So this is our main diagram for our implementation. We are focused actually on MAC merge sublayer or MMS. Here we can see how it is structured. So our implementation of MAC merge sublayer is structured into express filter, which is used to differentiate between preemptible and express traffic, receive and transmit module, which is responsible for preempting and merging already preempted frames. This image shows an actual screenshot from our implementation in Quartus, a software tool for design. So we can see that it fully corresponds to the previous diagram. Finally, we provide a floor plan of our implementation. In red, our design is marked, so we can see that very little resources is actually reserved from this component. I think you can find it in the paper, but it is less than 1% of the resources. Here are some basic information about implementation. So it is designed using VHDL, targeting Intel FPGA Cyclone 4 platform. So this is the low-cost platform. The design was verified using UVM and industry standard verification tools. Used software is listed here, so we use Python for some data processing and visualization, and these two tools for design and implementation. We conducted a random test with randomized payload for both traffic types and variable length with randomized sending time of express traffic. This is our verification environment according to UVM methodology. There is, of course, MAC merge sublayer is device under test or DUT, and many other components to support this test. So we have components such as monitor and driver that enables sending stimulus to the DUT and also collecting responses from the DUT. Scoreboard component is responsible for comparing the obtained results with the expected results. And coverage module is responsible to give us an answer how many test cases we actually covered by our test. These are the results reported from our random test. So we sent 800 transactions of express traffic in total and 400 transactions of preemptible traffic in total. So on the right side, we can see the coverage report. So we can see that preemptible traffic contains many cases, which is natural because we wanted to cover many different cases when preemptible frames are actually preempted. So basically, to conclude this presentation, we presented an implementation of frame preemption mechanism on a low-cost FPGA platform. It was verified by industry standard methodology and tools, and in our future work, we plan to extend the implementation with MAC and RS sublayers and also add more tests and test the design on a real platform. Thank you for listening to this presentation. I will be more than happy to further discuss this topic and possibly answer a question. You can send that using this email. Thank you.